Moving on to the fifth graph of 8 is the cubed function. The cubed function simply is a variable x to the third power. So I'm going to plug in some random points and see what happens to those points. So when I plug in a 0 for x, I get 0 to the third power, which is in fact 0. So the origin will be a point on the cubed function. When I plug in 1 for x, I get 1. So the point 1, 1 is on my graph. So far, very similar to the squared function I did just before this. 2 cubed is 8. So 2, 8 is a point on my graph. So again, it starts to look very much like a parabola. It just happens to be a little more compressed, so it seems to shoot up a lot faster than the square function we did earlier. Let's see what's happening on the left side of the y-axis. If I put in a negative x, I get negative 1 to the third power. Well, a negative 3 times is still negative. So negative 1, negative 1. So it's not a parabola where the left side matches the right side. It is in fact going down since we do have negative y values. When I plug in negative 2 for x, we get negative 8. So negative 2, negative 8 is a point on my graph. So you can see that this graph is going to turn and go downward. So this is an example of the cubed function. Some of the characteristics about the cubed function. The x-intercept is again at the origin. This time the symmetry is origin symmetry. Everything in the first quadrant gets rotated around and is now in the third quadrant. Or you can think of it as two individual reflections. This would be reflected over the y-axis, and then what's up here would then be reflected over the x-axis. So two reflections also represent an origin symmetry. You can see that this graph, as I moved from left to right, I am increasing over the whole interval. It's continually going up the whole time. So it is increasing over the interval from negative infinity to positive infinity for x. It is never decreasing. The domain is all real numbers, because you can see it starts at negative infinity and it goes all the way to positive infinity. And the range starts at negative infinity and goes to positive infinity as well. So those were 6 basic functions. Let's look at the last 2. Another basic function is what's called the reciprocal function. The reciprocal function is 1 over x. So let's put in some values of x and figure out what we will get for y. So let's try 0, 1, and 2. Let's start with those. And negative 1 and negative 2. So 0, if I plug in a 0 for x, what do I get? Well, 1 divided by 0, oh, that's undefined. There is no point at 1 over 0. You cannot do that. So there is no point. If I plug in 1 for x, I get 1 over 1, which is 1. So I'll have a point at 1, 1. What if I plug in 2? 1 over 2 is 1/2, or 0.5. So 2 and then 1/2. 2 and then 1/2. You can see it's getting smaller. Let's put in, before I do negative 1, let's put in a 3. Let's put in a 3 there and see what happens. If I do 1 over 3, we get 1/3, which is 0.3. So we have a point at 3, 1/3. So 3. So these are just getting smaller and smaller and smaller and smaller like that. But what's it doing in between 0 and 1? That I would like to know. So let's put in a point between 0 and 1. Let's actually put in a 1/2 for x. If I put in a 1/2 for x, I'm trying to find a point like right in here and to see what it's doing. If I put in a 1/2 for x, that's 1 divided by 1/2. And we know when we divide fractions, you actually flip the bottom fraction and multiply. So when I flip the bottom fraction, I actually get 2 over 1, which is 2. So I'll have a point at 1/2, 2. So right here at x is 1/2, it actually becomes 2. So what this graph is going to end up doing is it's going to hug the y-axis on the left. It's going to hug the x-axis on the bottom. So let's now see what's going to happen on the negative side. I didn't leave myself much room, but I think we'll only need a couple points to determine what it's going to look like, especially if it has some symmetry. So let's start with -1. 1 over -1 is -1. If I plug in -2, 1 over -2 is -1/2. So -2, -1/2. Oh, I see. So it's going to do the same thing on this side. As it did on the right side. So this is an example of the reciprocal function. Notice that x can never ever be 0. Okay, so if we looked at my domain, x can never be 0. And if you look at this picture, the only place where x is 0 is right here. And if I drew like a little line right here on top of the y-axis, you'll see that this graph never ever touches x is 0. It'll just keep getting closer and closer and closer to the y-axis, which is where x is 0, but we'll never touch it because it can't, because x cannot ever be 0. So the x-intercept on this graph is, oh, there isn't one. Okay? The function has the following symmetry. So you can see it does not have y-axis symmetry, it does not have x-axis symmetry, but it does have origin symmetry. Now if we look at the increasing and decreasing, let's start over here on the left. As I move from left to right, this graph is falling, falling, decreasing, 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 decreasing. So it is decreasing from -infinity all the way up to 0. Over here on this side, starting just on the other side of the y-axis, just on the other side of 0, the graph is also decreasing, 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 and it's still decreasing forever and ever. So not only is it decreasing on the left of the y-axis between these intervals, but it's also decreasing on the right-hand side of 0. But we split that up into two separate intervals since it's not continuous. It is never increasing. The domain goes from -infinity to 0 and then picks up on the other side of 0 and goes to +infinity. The range does the same. Starts at -infinity, goes to 0, picks up on the other side of 0, and goes to +infinity. The last graph is called the constant function. This is probably the easiest of them all, where f of x equals some number. This is a constant. It could be any number. It could be 2, it could be -10, it could be pi, it could be any constant number that does not change. Notice there is no variable in here. So there is technically no x to ever plug in. So no matter what x is, I could plug in a 0, a 3, a -10, a 100. It wouldn't matter what I plug in for x. Y will always give me b, whatever b is. If b is 10 or pi or 0, it will always give me that number. So all of these points are going to be at 0, b, 3, b, -10, b, 100, b, and so on. So if I try to graph these, let's just create a b. I don't know where b is. Let's just say this right here is b. So I'll have a point at 0b, which is right here. I'll have a point at 3b, which is right here. I'll have a point at -10b, which is right here. I'll have a point at 100b. So you can see by now that this is going to create a horizontal line. Through the y-axis at the number b. So some of the characteristics about this graph, the x-intercept is, well, there will not be one. The only time there could be an x-intercept is if this graph was actually lying on top of the x-axis. So if this graph actually was y equals 0, then this graph would lie right on top of the x-axis. So it would have infinite number of x-intercepts since the whole line lies on top of the x-axis. That's a very unique case. The y-intercept is obviously at b, so it'd be at 0, b. The function has the following symmetry. You can see everything on the right side is an image of the left, so that means it has y-axis symmetry. The graph is never increasing, nor is it ever decreasing, because this is a constant function. It remains flat. The domain goes from -infinity to +infinity. And the range starts, the first place I see a y value is at b, and that is the only place I ever see a y value. So we would describe it as y can be any value as long as y is b. Y is never any other value. So those were the 8 functions that I suggest you memorize and keep those handy. If you'd like to put them on a cheat sheet, something like this, that might be advantageous, so that way you can quickly refer back to it. So all of these functions are what we just went over, and those are something that you'll probably want to, again, have memorized. So I just want to kind of put all of this together in just 2 examples, just to recall what we've already done. And in here we're going to graph some of the functions that we've already been talking about on a graph. We're going to be discussing piecewise functions, where you'll see part of one graph, maybe a square graph, and then maybe a cube graph, or maybe an absolute value combined with a reciprocal. So we're going to combine different functions together in one graph, and that's called piecewise. So pieces of one graph plus pieces of another. So the function is said to be continuous if its graph has no gaps or no holes. So no gaps and no holes, and it basically can be drawn without ever lifting your pencil from the paper. For the following functions, let's define the domain, range, intercepts, whether it's continuous, and then we'll also graph the function. So here's my 2 pieces. I've got one piece up here. I'll put this part in red. And then I've got another piece of the graph here, and this part I'll graph in green. So the first piece I'm going to graph is a linear. You can see that this is y equals mx plus b. It's just a line. And I'm going to graph that for anywhere that x is less than 1. So what I'm going to do is I'm going to put a piece of paper over the part that's not involved. So this is only when x is less than 1. So I'm actually going to put this little piece of paper over anything that's greater than 1. I know that side of the graph is not going to be used. So only when x is less than 1, I'm going to graph this line. This line has a y-intercept at 3 and a slope of -2. So that's down 2 to the right 1. Or I could go up 2 to the left 1. So you can see that this is going to be a straight line. I'm going to connect these pieces together. This piece of my function will look like this. Now notice the endpoint is not included. This is only for when x is less than 1. So I'm actually going to show a hole at the endpoint right here, because that point is not included. Now in this part over here, I'm only looking at the part of the graph that's to the right or greater than or equal to 1. So now I'm looking at this part of the graph. So now I'm only looking at anything to the right of 1. So from here to the right. Okay? So I'm not going to look at anything to the left of this piece of paper. So using this y equals mx plus b, we're going to graph this linear function starting at 1 and moving to the right. So the first place I look is the y-intercept, which is -2. The y-intercept actually is back here at -2, but I'm not actually going to draw that, but it's just going to help me to get my position. From this point, I'm going to have a slope of 3. So that means I go up 3 and over 1. So that's actually going to meet my graph. So my graph will start here. That point will be included, so I'm going to color it in because that point you can see is included at 1. Then I'm going to move to the right from that point. So if this point is included, I have a slope of 3. So I'm going to go up 3 over 1, up 3 over 1. And then when I connect these points together, this is the graph that I'll have. It's basically a V, but it's got two different slopes on each side. Some of the things I was asked to find is first the domain. To find the domain, you can see that this graph starts at -infinity. It comes down, it keeps going all the way up to +infinity. So this graph goes forever and ever to both x's on each side. So the domain is all real numbers. The B says write the intercepts. The intercepts. There is no x-intercept. There is only a y-intercept, and it looks like it crosses at 0, 3. C. Graph the function. Already did. D. Find the range. The range, the graph starts in the y direction. It starts at the number 1 and goes to +infinity. And part E says, is it continuous? Well, it's continuous if I never had to pick up my pencil. There can be no holes and no gaps. And you can see I could continuously draw this. Since I colored that in, it does continue in the right direction. So yes, it is continuous. And all over the total domain, which was from -infinity to infinity. So let's try one more. This time my piecewise function looks like this. So the first part of my function I will graph again in red, and the bottom part I will graph in green. The first part in red is only when x is less than 0. So I'm going to put my piece of paper over all of that where x is not less than 0, and I'm going to graph this piece here just on the left-hand side when x is less than 0. Well, you can see that this is mx plus b. They're just written in reverse order. So b, the y-intercept, is at 4. which is here, but I'm going to show an open circle because 0 is not included right here. Then my slope is 4. From this point I have a slope of 4. So I'm going to do a slope of 4. So 1, 2, 3, 4 over 1. 1, 2, 3, 4 over 1. So I connect those pieces together. So that part of my graph is this part, this piece of the function. Then I'm going to graph the bottom portion, the green portion. That's only when x is greater than or equal to 0. So I'm actually going to cover up this left side. I only want the part of the graph where x is greater than 0. X squared, well, we know what the x squared graph looks like. It is a parabola going through the origin. So I'm going to start at the origin, and I will actually color that in since it can be included. And then I draw my parabola. Remember, the parabola has points at the origin, 1, 1, 2, 4, and then we can just connect them together. Notice this is a function. A function is determined by the vertical line test. Anywhere I draw a vertical line, it will only pass through the graph one time. Even if I draw a line right down the y-axis, I will not touch the graph until I get to this point right here, so it only hits the graph one time. That's why it's important that we show an open circle here and a closed circle here, so that way it does in fact pass the vertical line test. The domain of the function starts at negative infinity, actually goes all the way to positive infinity. All numbers are included. The intercepts, it has an x-intercept at the origin, and the y-intercept is also at the origin. I graphed the function. The range starts at negative infinity, and it actually goes all the way up to positive infinity. So all real numbers. And then for part E, is it continuous? Since there is a hole right here, and I did have to physically lift my pencil up because I drew this part of the graph, then I lifted my pencil up, put it back down to draw the other side, this is not continuous. I did just think of one other thing. When we were talking about the intercepts, the x-intercepts, there's actually a second x-intercept that I didn't see until just now. There's an x-intercept at the origin, but there's another one. This is an x-intercept also. So also at negative 1, 0.